In this video, we will learn about R2R ladder network digital to analog converter. Let us consider a simple network. A network which consists of three voltage terms V1, V2, V3. Output of this network is denoted as V0. Let V01 be the output of this network when input V1 is considered and the other two inputs are replaced with its internal resistance. Let V02 be the output of this network when only V2 is applied. The other two input voltages V1 and V3 are replaced with its internal resistance. And let V03 be the output when only the third input signal V3 is considered, with the other two input signals V1 and V2 are replaced with its internal resistance. So according to superposition theorem, we can write V0 is equal to V01 plus V02 plus V03, where V0 is the output of this network when all the three input signals are applied, and V01, V02 and V03 are the output voltages when only V1, V2 and V3 are applied, with the other two voltage sources replaced with its internal resistance. Now let us discuss the limitations of a binary weighted resistor digital to analog converter. One of the simplest form of DAC is binary weighted DAC. Even though the circuit is very simple, the binary weighted resistor network consists of resistors whose value are binary weighted values of other resistors. Due to this reason, this type of DAC is less preferred compared to R2R ladder network DAC, which contains resistors of only two values R and 2R. R2R ladder network digital to analog converter. R2R ladder network digital to analog converter consists of a network which resembles a ladder. The ladder network contains resistors of two resistance values R and 2R, unlike a binary weighted resistor network digital to analog converter. This type of digital to analog converters are preferred to be implemented in integrated circuits, as binary weighted resistance values are not required for its implementation. This is the circuit diagram of a n-bit R2R ladder network digital to analog converter. Non-inverting input of the operational amplifier is connected to ground, and there is a feedback resistance 2R connected between output and inverting input. So here the operational amplifier is connected as an inverting amplifier. There are n number of inputs from D0 to Dn-1. D0 is the LSB and Dn-1 is the MSB. The ladder network consists of resistance of two values R and 2R, as we can see in the diagram. This is the circuit diagram of a 3-bit R2R ladder network digital to analog converter. The inputs are D0, D1 and D2. Whenever an input is equal to 1, the corresponding switch is connected to plus VR, and whenever an input is equal to 0, the corresponding switch is connected to ground. The circuit diagram of a 3-bit R2R ladder network digital to analog converter is shown. The circuit consists of an op-amp in inverting mode as its non-inverting input is connected to ground, and a ladder network connected to the inverting terminal. The switches D0, D1 and D2 connects a reference voltage VR to the R2R ladder network. The corresponding bit is high, else that switch is connected to ground. Output voltage of a R2R ladder network digital to analog converter. For a n-bit digital to analog converter, there are 2n input combinations. For a 3-bit digital to analog converter, there are 8 combinations from 000 to 111. According to superposition theorem, output voltage of the DAC can be written as sum of outputs for various input combinations with only one of the n bits of the input combination set as high. For example, if input is 101, the output can be written as sum of the outputs of DAC when its input is 100 and output of DAC when its input is 001. To find the expression for output voltage of a R2R ladder network digital to analog converter, first step is the application of superposition theorem. Find the response of the circuit with only one of the n inputs set as high. If n is equal to 3, input combinations are 001, 010 and 100. Add these n number of expressions or equations to get the final expression for the output voltage of n-bit R2R ladder network digital to analog converter. We can write V0 is equal to V01 plus V02 plus V03 plus etc. V0n, where V01 is the output of the R2R ladder network digital to analog converter, where V01 is the output of the R2R ladder network only when the LSB bit is set as 1 with the remaining n-1 bits set as 0, and V0n is the output of the R2R ladder network digital to analog converter only when MSB bit is set as 1 with rest of the inputs are set as 0. In our example, as n is equal to 3, we have to find 3 equations for output voltage. Equations for output voltage when inputs are 001, 010 and 100, and add these values to get final equation for the output. If n is equal to 4, then the input combinations we have to consider for application of superposition theorem are 0001, 0010, 0100 and 1000. Find the equations for the output voltage for each of the above combinations and add these expressions to get the equation for output of R2R ladder network digital to analog converter. Case 1. When all the 3 inputs are set as 0. Here we can see the 2 resistors of value 2R are connected in shunt, which is shown in the yellow colored box. So we can reduce this network as shown. So 2R and 2R are in shunt. So the parallel combination is replaced with a resistance of value R. This resistance R is in series with a second resistance R, which is shown in the yellow colored box below the green arrow. So we can combine these two resistors of value R. The equivalent value becomes 2R. Now this 2R is in shunt with another resistance of value 2R. So we can replace the shunt combination with the resistance of value R. We can further reduce the circuit as shown. Finally, we will get an inverting amplifier with input Vi is equal to 0. So output of the inverting amplifier V0 is equal to 0 as input voltage is equal to 0. Now case 2. When D0 is equal to 1, D1 is equal to 0 and D2 is equal to 0. This time we are setting the LSB bit as 1 and the other two bits are set as 0. So when D0 is equal to 1, corresponding switch is connected to reference voltage plus VR, so the circuit can be redrawn as shown. Now we will apply Thevenin's theorem. To apply Thevenin's theorem, we have to divide the circuit into two networks, network A and network B. Then disconnect network B from network A. Find the Thevenin equivalent voltage of network A and Thevenin equivalent resistance of network A. We will get Thevenin equivalent voltage is VTH is equal to R by 2 and Thevenin equivalent resistance is RTH is equal to R. So now we will replace network A with its Thevenin equivalent. After redrawing the circuit becomes as shown below the red arrow. Now we can combine the two resistors of value R which are in series. So equivalent value is equal to 2R. Now again we will apply Thevenin's theorem. Divide this network into two networks, network A and network B. Find the Thevenin equivalent of network A, VTH and RTH. This time we will get VTH is equal to VR by 4 and RTH is equal to R. We will replace network A with its Thevenin equivalent as shown below the red arrow. Again we can see that the two resistors R and R are in series. R of network A and the neighboring R of network B are in series. So we can combine these two resistors to form the effective value as 2R. Again we will apply Thevenin's theorem. So again network A and network B. Network B is disconnected from network A. Finding the Thevenin equivalent of network A, we will get VTH is equal to VR by 8 and RTH is equal to R. So here we will replace network A with its Thevenin equivalent, which is a series combination of VR by 8 and R. Now we can combine the two resistors of value R to make the effective value as 2R. So now we can see that the circuit is reduced to an inverting amplifier with gain -1 and input voltage of the inverting amplifier is equal to VR by 8. So effective output voltage is V0 is equal to minus VR divided by 8. R2R ladder network is reduced to an inverting amplifier with gain -1. Input voltage to the inverting amplifier is VR by 8. So equation for output voltage when digital input is 001 is -1 into VR by 8, that is equal to minus VR by 8. Now let us consider the third case. D0 is equal to 0, D1 is equal to 1 and D2 is equal to 0. So as D0 and D2 are equal to zeros, the corresponding switches are connected to ground, and as D1 is equal to 1, the corresponding switch is connected to reference voltage plus VR. So we can redraw the diagram of a 3-bit R2R ladder network digital to analog converter as shown. Here we can see the two resistors on the extreme left of values 2R are in shunt. So we can combine these two resistors of values 2R to a single resistance of value R. Here above the red arrow, we can see in the yellow box, the two resistors of value R are in series. So we can combine these two resistors to form a resistance of value 2R, and the diagram is shown below the red arrow. Now let us apply Thevenin's theorem. Divide the network into two networks, network A and network B. Disconnect network B from network A. Find the Thevenin equivalent of network A. We will get Thevenin equivalent voltage VTH is equal to VR by 2 and Thevenin equivalent resistance RTH is equal to R. Now here we will replace network A with its Thevenin equivalent. So the circuit becomes as shown below the red arrow. Here the two resistors of value R are in series. So let us combine these two resistors to make a single resistance of value 2R. Again we will apply Thevenin's theorem. Divide the network into two networks, network A and network B as shown in the diagram. Find the Thevenin equivalent voltage and Thevenin equivalent resistance of network A. We will get Thevenin equivalent voltage VTH is equal to VR by 4 and Thevenin equivalent resistance RTH is equal to R. So now we can replace network A with its Thevenin equivalent, which is a series combination of voltage VR by 4 and resistance R as shown below the red arrow. In this diagram, we can combine the two resistors of value R to make a single resistance of value 2R. Now the circuit becomes an inverting amplifier with gain -1 and the input voltage of this inverting amplifier is equal to VR by 4. So the R2R ladder network is reduced to an inverting amplifier with gain -1. Input voltage to the inverting amplifier is VR by 4. So equation for output voltage when digital input is 010 is -1 into VR by 4, that is output voltage V0 is equal to minus VR by 4. Case 4. When D0 is equal to 0, D1 is equal to 0 and D2 is equal to 1. As D0 and D1 are at logic 0, the corresponding two switches are connected to ground. As D2 is equal to 1, corresponding switch is connected to reference voltage plus VR, so we can redraw the circuit as shown. So here in the diagram we can see that two resistors of value 2R are in shunt as shown in the yellow box. So we can combine these two resistors to a single resistance of value R. Two resistors of value R are connected in series. So let us combine these two resistors to a single resistance of value 2R. Here we can see above the red arrow, the circuit consists of two resistors of value 2R connected in shunt. So we can combine these two resistors to form a single resistance of value R as shown in the diagram below the red arrow. So again the circuit can be reduced as shown below the red arrow. Now apply Thevenin's theorem to the circuit. Divide the network into two networks, network A and network B. Disconnect network B from network A. Find the Thevenin equivalent of network A. So Thevenin equivalent voltage of network A, VTH, is equal to VR by 2, and the Thevenin equivalent resistance of network A, RTH, is equal to R. So we can replace network A with its Thevenin equivalent. Now the circuit is reduced to an inverting amplifier with gain minus 2R divided by 2R, that is equal to minus 1, and input of the inverting amplifier is equal to VR by 2. So equation for output voltage when digital input is 100 is minus 1 into VR by 2. So output voltage V0 is equal to minus VR by 2 when the MSB is set as 1 and the other two bits are set as zeros. Now let us find the general expression for output voltage. So we had derived equations for output voltage for a 3-bit R to R ladder network digital to analog converter. For three different input combinations, V0 is equal to minus VR by 8 if input is 001. V0 is equal to minus VR by 4 if input is 010. And V0 is equal to minus VR by 2 if input is equal to 100. So equation for output voltage for any input voltage can be written as V0 is equal to minus VR by 2 into D2 plus minus VR by 4 into D1 plus minus VR by 8 into D0. So this is the expression for output voltage of a 3-bit R to R ladder network digital to analog converter for any input combination. So minus VR is a common term. So taking minus VR outside, we will get V0 is equal to minus VR into 1 by 2 raised to 3 D0 plus 1 by 2 square D1 plus 1 by 2 raised to 1 D2. So we can reduce the expression as V0 is equal to minus VR into 2 raised to minus 3 D0 plus 2 raised to minus 2 D1 plus 2 raised to minus 1 D2. So finally we can write for a 3-bit R2R ladder network digital to analog converter. V0 is equal to minus VR into 2 raised to minus 3 D0 plus 2 raised to minus 2 D1 plus 2 raised to minus 1 D2. Similarly, for a 4-bit R2R ladder network digital to analog converter, we can write V0 is equal to minus VR into 2 raised to minus 4 D0 plus 2 raised to minus 3 D1 plus 2 raised to minus 2 D2 plus 2 raised to minus 1 D3. In general, in the case of a n-bit R2R ladder network digital to analog converter, we can write the expression for output voltage V0 as V0 is equal to minus VR into 2 raised to minus n D0 plus 2 raised to minus n minus 1 D1 plus etc. plus 2 raised to minus 1 Dn minus 1. Now let us consider the example of a R2R ladder network digital to analog converter with input 1, 0, 1. So this is the diagram of a R2R ladder network with input 1, 0, 1. As D2 is equal to 1, corresponding switch is connected to reference voltage plus VR. As D1 is equal to 0, corresponding switch is connected to ground, and as D0 is equal to 1, corresponding switch is connected to reference voltage plus VR. So output voltage V0 is equal to V01 plus V02 plus V03, where V01 is the output voltage when input is 001, V02 is the output voltage when input is 000, and V03 is the output voltage when input is 100. When input is 001, we will get output voltage V01 is equal to minus VR by 8. When input is equal to 000, the circuit will be reduced to an inverting amplifier with no input connected. So output voltage V02 is equal to 0. When input is equal to 100, we can reduce the circuit to an inverting amplifier with gain minus 1, and input voltage of the inverting amplifier is equal to VR by 2. So output voltage V03 is equal to minus VR by 2. So we had found that when input is equal to 001, output is equal to minus VR by 8. When input is equal to 000, V02 is equal to 0. And when input is equal to 100, output voltage V03 is equal to minus VR by 2. Let VR is equal to 8 volt. Therefore, we will get V01 is equal to minus VR by 8, that is equal to minus 1. V02 is equal to 0 and V03 is equal to minus VR by 2, that is equal to minus 8 by 2, that is equal to minus 4. Therefore, output voltage V0 is equal to V01 plus V02 plus V03. Output voltage V0 is equal to minus 1 plus 0 plus minus 4. Output voltage V0 is equal to minus 5 volt, which is the analog equivalent of 101. Thanks for watching Circuits Analytica. Enjoy learning. Please comment, share and subscribe our channel.